Okay. You can stay. No? Okay. Try and finish your words. Yeah, so you'll notice this isn't a barbecue. Talk a little bit more about that in a bit. But what this is a beginner session for the June 2018 meeting. So my name is Brendan. I will be talking about galaxies. In retrospect, I probably should have done one on observing Mars this month, but I don't know. Time is relative, you know, and the information contained within this presentation will still be good for plenty of time to come. So, what are galaxies? So, what we know them as, and there's going to be a lot of discussion of just even things like classification and whatnot. But in general, galaxies are massive gravitationally bound systems consisting of stars, stellar remnants, interstellar medium, gas and dust, and probably, or whatever, dark matter, right? Just like most of the rest of the universe, assuming it actually exists, and it's not just some, we forgot to carry one somewhere. Yeah, so we'll get into the specifics of it, but that is generally what we're talking about. So if you imagine, you know, way back in the early days, you know, of astronomy, we didn't know the galaxies existed, right? But we did know, but we did observe galaxies. So if you go back as far as 964 CE, there were recorded observations of what we now know as the Andromeda Galaxy. It is a naked eye object. You can see it. You can see it. Come on, Jay. Come on. It's okay. Former president, you can do that. So at least I hope I can when I'm done. But we observed. So we were actually able to observe the Andromeda Galaxy, make recordings of it, and like I said, it is a naked eye object. It's something you can go out in a good dark sky and see with the naked eye. It's a little bit of a fuzzball, but you know, almost like an out-focused star. But it's definitely observable. So it was actually recorded, but they didn't know what it was, right? It was made mention of, and that's it. So the actual in this almanac that was written in 964, this is Sagittarius. I couldn't find the page that actually had Andromeda on it, unfortunately. Going through historical text is really challenging. I don't know how the historians and archaeologists do it, but anyway, and I have the internet. But it was described as a little cloud. So now the Milky Way, in some respects, is a big cloud. If you are looking up in the nights in a good dark sky, you will see, I mean, not exactly this, but you will see the wispiness and the milkiness of the Milky Way, right? And the reason why it looks milky like that is just because it's just full of stars, right? There's dense populations of them, but they're also far away, so they're not those nice pinpoint lights, right? So you know the nice bright points of light that you see here, right, in and around this area are actually close to us, right, or closer to us than the rest of the Milky Way, generally speaking. Right? So this is something that we were able to look up at and see, right? So as time went on, you know, you can look at this Milky Way and basically say, this is different than the rest of the stars that are out there. They behave differently than the planets that we've identified and observed. So what's different about them? Or what is different about it, right? So, and there was some debate about this. You know, like I said, that milkiness, they're not clearly stars, right? So is the Milky Way actually filled with it? It's kind of this wispy, nebulous, you know, kind of thing, right? Now, we can use a technique called parallax, which is basically, if you imagine, I'll use this. Oh, this isn't going to work very well. Let me plan this out. Use my arms as I usually do. So if you imagine me as the sun, and my left arm being the planet Earth, right? And as the Earth is orbiting around the sun like this, what I can do is, at this point in the orbit and this point in the orbit, I can actually make an angle with a distant object. And we've been able to do this for quite some time. It's pretty easy once you understand the math. It's not that complicated. It's high school trig, right? So once you have that figured out, you can basically do some quick math to be able to judge the distance to an object fairly easily. Now you can't see very, very far with this. There's a limit to how good parallax is and how far you can use it to tell the distance of something, but early astronomers were able to do this. And basically, they were able to determine that parts of the Milky Way are very, very far away. That's about all they knew. You got all sorts of different takes on it. I'm sure that this guy was well respected and thought that everything he said was correct. And he said there was an optical effect due to our version of what appears in what locally approximates to a flat layer of stars. I mean, pretty good intuition, right? It's generally true. There's also, but there is also this kind of, especially at the time, the Earth-centric universe, kind of idea. But they knew that there was this growing belief that these points of light were stars. Telescopes really help that. Because if you've ever, even just with a pair of binoculars, just look at the Milky Way, right? It goes from being this kind of wispy, kind of like out of focus cloud to points and points and points and just, hundreds of points of light, in your field of view, right? So you will see stars, right? Maybe not hundreds, it's a bit of an exaggeration. If you happen to catch a good star field, definitely, but regardless. But that you will see many, many points of light, right? And so as early astronomers built their telescopes and as they were looking deeper and deeper, they really started to notice that this Milky Way was really just consisting of stars. Now, of course, getting back to the Earth-centered thing, this was an early map that was put together. Of course, it only makes sense that that our solar system is at the center of it. You do notice there's a couple things. There is evidence of, they can kind of tell there's probably some spiral arms. And this was basically just done by looking at counts of stars in various directions, right? So being far enough outside of the Milky Way, we're actually able to do that. Of course, they put us right at the center. Very happy that wasn't true, because there is a giant black hole likely sitting right around there. But this was a fairly early attempt at it, right? Now, so we now know at this point in history that the Milky Way is just a collection of stars that we are looking into, right? Now, also at the time, we were looking outside our galaxy, right? And outside our galaxy, we were observing nebulas and galaxies. If you didn't know anything, and I showed you this versus this, you might be able to tell the difference a little bit, but not really, right? I mean, we all have the bias now that we do know that this is a galaxy and this is a nebula, but to the naive eye, that is mostly meaningless. Like, you can't really judge them. So the debate at the time was, are these objects in our galaxy, or are they actually other galaxies potentially? Which is a groundbreaking kind of idea at the time, right? It basically goes from our existence, being in this collection of stars to we're just another collection of stars in a universe filled with other collections of stars. The one focal point of this debate was what was called at the time the Great Andromeda Nebula. And the one thing about Andromeda is it's pretty easy to pick. Once you get enough telescope power, it is pretty easy to identify individual points of light within it. So you can kind of tell that there are stars in it. And it became a little bit of like, well, maybe it's just orbiting not too far away. We didn't have a good way of telling the distance to it. Parallax didn't work. We weren't able to quite tell. We weren't able to resolve things well enough to really be able to tell distance to it. And so this led to what was called the Great Debate in 1920. Jerry, if you ever want to do a talk on this, I don't know if it's your interest or not, I'd love to hear more about it. Just throwing that out there. Sure. Yeah. But based on just the brief rundown of it was that there were basically two camps. Pro-nebula, meaning that our galaxy is the only galaxy, that's it, end of story. Pro-galaxy, Curtis's side, was we are in a galaxy, and it's nothing special. There's plenty of other galaxies out there that we have observed, and we're just not calling them galaxies, right? And there was a kind of what happened was that evidence started to bend in one direction, right? And when you start looking at, like, there were some things that kind of threw things off. So Andromeda not being part of the Milky Way implied its distance was on the order of 10 to the 8 light years. It's very far away, right? That is, they couldn't believe it at the time, that such distances could even exist, but they do. And the other one that was observed was Van Manen, Dutch observer, had observed M101 rotating. And what that would mean is that it's actually close and fast moving and nearby, right? Turned out he didn't observe that. That's just. But there were observations showing that the Andromeda Galaxy looked a heck of a lot like our Milky Way, but if we were to be observing it from outside of the Milky Way. Right? So that got some people suspicious, and Hubble, who I didn't actually time it like this, but Hubble will be coming up a few more times tonight. But Edwin Hubble was able to observe these stars called Cepheid variables in the Andromeda Galaxy. And Cepheid variables are really special stars because they have a known light curve. And using that, so they have a brightness, like they're variable stars that fluctuate their period, their luminosity over a given period. Basically, because of that fact, we can use them as what we call standard candles. We can tell, just by observing them and comparing them to something else nearby, we can tell how far away that is. It's a really, really nice element of how the universe works, because we'd be hooped in some ways without it, or we would have been hooped in some ways without it for a little while. So Cepheid variables are really special for that reason. And being able to resolve individual Cepheid variable stars in the Andromeda Galaxy is really what put the nail in the coffin of the idea that it wasn't another galaxy. So these findings were presented in 1925, and that's kind of how we got to our current understanding today. So like I said, galaxies are anywhere from, even the closest galaxy, which we refer to as the Large Magellanic Cloud, another naked eye one that you can see, but it's in the southern hemisphere, 160,000 light years, all the way up to M87, which is 53 million light years away, right? So it is, they are far. It's a long way to go. Now, as astronomers, as science just seems to happen, we classify things. So we classify galaxies into elliptical. We classify them into spiral, and then we just gave up and said, fine, there's irregular ones. The predominant difference is that spiral galaxies, you got the arms, right? Elliptical galaxies, you don't. The elliptical galaxies are also tend to be much larger, older. They don't have, I'll talk about this a little bit later, but there's star-forming regions, we call them, so we call H-alpha areas, so you can kind of see that gas. These are nebulous clouds of gas that will eventually form stars. You don't see a lot of new star formation in elliptical galaxies. So this is kind of nice to know about. And then, being the way that we are, we decided, hey, yeah, sure, let's classify it even more. So this breaks down into the elliptical side. So these are all the elliptical ones. These are the spiral ones. There are kind of like cross galaxy kind of classification. It's almost like it's a spectrum, right? So it's not like there's some binary switch between these two types. They're just generally they're on a spectrum that's just kind of how they get slowly broken down a little bit. You'll notice these numbers. These indicate for the elliptical ones, this is how elliptical they are. So 0, kind of like a circle, and then we get up to 7 is very long, very elliptical. There's two types of spiral galaxies. There are the ones without the bar, and then the ones with the bar. So you can see the bar there, right? And that's what that B indicates, right? So there's a bar there, and then the spiral arms coming out of that. And then how I don't know, unspirally they are determines like what this letter is. So in this is this kind of elongated kind of spiral. Anyway, so that's how you get into those things. I talked about all this. So some examples of elliptical galaxies. So M60 and M59. So you can kind of see this one is a lot more round. So that's why it's step 2. This one's a little more elongated. Step 5. Spiral galaxies, I talked about a lot of this too. You've got a flat rotating disk of young stars in interstellar matter, central stellar bulge right there, and a near spherical halo of stars, and a supermassive black hole at the very center of the large bulge. So I think every single galaxy we have looked at of this type, we have found a black hole at the center. Or an endless hole anyway. Oh yeah, right, the word I was looking for was woundness. How winding, or how much windiness is there to the galaxy? I'm really good with words tonight. But if you get just breaking this down a little bit further, yeah. So if they're tightly wound, then you have the A, and then B and C. So you get more loosely wound. And the bulges do kind of make a difference a little bit too. So. But that's not good enough. Okay, so let's step it up a little bit. We can break things down even further. So this is just to show you that like there are just as science treks along and as we add more and more classifications to things, that we get a little bit more in depth. You'll never have to worry about this, but it's just funny to me that it exists because it's going to exist. That's how it works. But they've actually so this system adds a bunch of things like ring classifications and whatnot. There's an expanded spiral arm classification, diffuse, broken arms, irregular, highly irregular. One of the other things about galaxies that I'll talk about in a bit too is that they actually tend to interact with other galaxies quite often. So you can see that quite often, and that tends to lead to things like arms being broken and whatnot, and various irregularities. And if you're going to throw it all together on a fun chart, this is a chart that you can look at. So basically, you move from ellipticals over here to lenticulars, spirals, irregulars, whatever. Anyway, so lots of classifications. So let's actually work through some exercises, because that sounds fun. Yeah. So but let's see a 77, just to show you that this actually has, so it's a way for us to basically define how these galaxies look. So the SA, right? So there's no real bar there. The RS means that it's the transition for a ring class galaxy, and the B is just it's not that tightly wound, but it's not that loose either. And you see 1300, definitely a bar, right? Very very barred. So we got the SB. The S denotes no rings, and more tightly wound than B, but less tightly wound than C, generally. Right? So that's what we got, BC. And you see 1672, definitely a bit of a bar, right? And yeah, tightly wound, more tightly, again, it's another BC, more tightly wound than B, but not less tightly wound than C. You don't tend to see a lot of the loosely wound ones, but so the spiral structure. So there's a bit of a problem with galaxies right now. Well, probably always have been for most universes, life. In that, when you look at a spiral galaxy, you kind of expect it to. You kind of expect things to break down after a little while. If you look at how the spiral structure is set up. And so one of the things that you would basically, if you were to just follow standard Newtonian physics, you would expect a galaxy over time to move from that nice spiral structure into this kind of circular, wound up kind of path, right? But what we actually see, that's actually, obviously that's not what happens, right? Like this wouldn't happen, otherwise most of the galaxies that we would see would actually be in this state. So what we actually see is this density wave kind of model where you can actually see the stars slowly flowing out, right? So that's actually what's going on right now. But that's a bit of a problem because as far back as 1959, things don't really quite jive with our understanding of physics. So basically what's been proposed is dark matter. There's this idea of modified Newtonian dynamics, which, and then also modified gravity. Basically, we have to change our laws of physics, or we have to add some factor. That factor right now is dark matter, right? And that's kind of the only. Right now, it's about the only, it's more widely accepted explanation, but it still is kind of. It's very hand-wavy at this point still. Yeah, but we've got quite a few different types of galaxies to look at. So there's lenticular galaxies. I mean, you'll never see this with your scope, but there, like I said, there's some irregular kind of types out there. This is a bit of an intermediate between an elliptical and a spiral galaxy. So kind of a weird one. There's this concept of a type SO galaxy that I was talking about earlier. So you kind of end up with, it has that ellipticalness, so it's almost like the age of galaxy is such that you have a lot of old stars near the center, but you still kind of have that spiral structure that's carrying along, right? It's also possible that it's amassed a lot more. It may have collided with another galaxy at some other point and amassed a lot of stuff. So, and just in the same way that we have dwarf planets, we have dwarf galaxies. It doesn't mean that they're any lesser than the regular galaxies, but they're certainly interesting. But they're not quite big enough to have the structure of what we would call or what we would call a galaxy. Right? So examples of these are the small and large Magellanic clouds that you can see from the southern hemisphere. Yeah, but we've actually got quite a few orbiting us. Most of them are pretty hard to see, but they're out there. Radio galaxies. These are neat. They are, so radio, when I say radio galaxies, I mean these are galaxies that emit a lot of energy in the radio wavelength. Right? So radio being light, just at a different wavelength than what we see optically. So they are emitting a lot in that wavelength. Now it doesn't mean that they don't have visual component to them, but you can definitely see there's a lot more going on in the radio than there is in the visual. Right. This is actually always something like worth when you're looking at when you're observing a distant galaxy. I mean, it's going to mostly look like a faint fuzzball, right? Like you're never going to see this. But one of the things that I like to think about is given all the star forming regions in a galaxy where like all of this masses, right? So these H2 regions are, and as the gas clouds come together, you're really like in these arms, right? In these areas here, you are really seeing the birth of stars, right? And you get that locally, quote unquote locally, in things like the Orion Nebula, for instance, right? But here, you've got a massive thing to look at. Now, obviously, you're not going to see this through your telescope, most people's telescopes. But when you're looking at that faint fuzzball, like just think about the fact that you have just an immense amount of stars that are just being born there. And obviously, it's going to take a very, very long time for that to go on. But you're looking at such a large area that you're going to actually, you're kind of seeing that in action. Bit of a stretch, but I like to think about it. I think it's neat. One thing that you can certainly observe in a distant galaxy are supernovae. So when a star goes supernova, you can actually see it popping up, right? So this little green arrow points to where that star is, and then where it wasn't, and what it turned into, which is this bright point of light. So, And you can definitely observe. Some of them are dim, but they're definitely observable. So if you ever get noticed, I mean, if you ever do get notice of one, I mean, go have a look at it if it is visually observable through a telescope, because it's not going to last for long, you know. So scratch it off your bucket list. As I was saying earlier, we do get interacting galaxies. So galaxies tend to, I mean, just thanks to gravity, things tend to pull on things as they do, and as a result, galaxies collide. We are on a collision course with the Andromeda Galaxy in a few hundred million years or something like that. I forget what the time frame is on it. I'll be dead. Billions. Yeah. It's a long ways off, but it will happen. Now, at the same time, you may think that that would potentially mean our doom. Our sun will be getting pretty hot by then, and we'll likely, let's just pretend that everything was the way it was now, and we were not on a, you know, and we were about to collide with the Andromeda Galaxy, like tomorrow. It wouldn't actually be that bad. The distances between the stars are so great that there's very low chance of things actually colliding. But it would definitely throw a lot of things off. Would look really cool though. I mean, having the Andromeda Galaxy, like, you know, like right in the night sky, would be sweet. Anyway, the other fun thing with galaxies is that we've come up with a bunch of fun names for them. The history of astronomy is rife with a lot of just, I don't know, dull, boring stuff because like we discovered it a long time ago and it just has kind of boring names. A lot of galaxies we didn't discover until like the past, you know, within the past couple 100 years or even 100 years. So we get stuff like the Black Eye Galaxy, right? I don't think Herschel ever would have called this the Black Eye Galaxy, but things like the Sombrero Galaxy. It's fun. It's a sombrero. We have a tadpole galaxy. I don't entirely know how it looks like a tadpole exactly, but it's kind of a tadpole. You know, the starfish. Maybe. I don't know. And then we got lazy, and we got to the point where we decided, okay, fine, we're just going to name galaxies after things that we've already, other astronomical objects. Anyway, that is all I have. Thanks very much. Welcome to Not the Barbecue. Tonight is the June meeting for the Winnipeg RASC. You just watched my long, rambly discussion on what galaxies are and how they're classified, which I'm sure was riveting. But moving on, everything's up from here though, basically. Because we're going to go through some announcements, and there's some cool stuff that happened and some other fun stuff happening. Chris Gaynor, who's our guest speaker tonight, will also be, well, he'll be appearing as a guest speaker, but also appearing as the vice president of RASC National. So he's just been giving us an update from National. I have Jay in here for Lost in Space. I don't know if he was still up for it or not. Gary? Yeah, you're good? Okay. So Jay's in for that. I don't know where Brian is.
Right here.
Hey, you're hiding in a different corner. Okay, so that's cool. So we'll have Brian giving us a what's up in the night sky, and then Ian Cameron, who I did spot over there, will be providing us with a what's new in science of astronomy. We will take a break for delicious goodies and coffee or hot chocolate or juice, and then we'll come back and we'll launch into our feature presentation, which will be the history of the Hubble Space Telescope, which I'm really looking forward to. So, how did we get here tonight? Well, we had a guest speaker, and I didn't want to pass it up because I thought the subject was awesome, and I haven't seen Chris speak before, but I'm sure he's really good. No pressure. And yeah, well, what that meant though, because due to the timing of things, was that we did need to bump the barbecue to the July meeting. So next month, there will not be a meeting here. We will be having the barbecue out at Glenley. come by around 6 p.m. We will have barbecues. It is, and when I say it's barbecue, it's a potluck. Bring your food, but the barbecues will be there to cook it. So feel free to come by. If it's looking, I don't know actually what the phase of the moon is at that point, but if you want to bring your scopes out, you certainly can if the weather's looking good. So, if the weather is not looking good, I will definitely send out an email just to let you know what, if any, our changes of plans are. So I will be apprising everyone of that as it goes. Again, nobody here next month. Barbecue. On that note, I do want to apologize a little bit for last month. Things got a little disorganized with the number of people that signed up and the fire code restrictions. So if I really hope that nobody actually got turned away. If you did, please come talk to me. I'm really sorry about that. But it was a little hairy there for a bit, so I do apologize if things seemed a little disorganized. But I'm hoping it was mostly worth it. But just wanted to say not bad. Yeah. So, but in terms of other announcements, I have been in touch with Riding Mountain to do a possible observing event. They reached out, and I met with the organizer a few weeks back, and they're offering us perks, which is cool. There's also potentially there will be an honorarium to the RASC for as well. And yeah, so if you are interested in helping out, let me know. Just feel free to shoot me an email and let me know if you want to come. Right now, I had a couple people that had expressed moderate interest when I brought this up a little while back. But now that this is more solidified, we'll need to actually get some from some folks. We're also going to be working with Trevor from you may know from the Sprucewood Star Party. He's part of the Brandon area astronomical something or others, but they'll be out there with their scopes as well, so it won't just be us. This is going back a little bit because I didn't get to do this last month because we're at the planetarium. We celebrated Astronomy Day. We did it at the Indigo on Keniston. It was an excellent turnout. I heard something like 200 people, and we got all these cute pictures like this. I don't know, it's just awesome. Like seeing kids like looking through scopes like that is just, I don't know, it's great. Makes me happy. And it sounds like we reached out to a whole bunch of people, and it was a generally pretty good success. Over the May long weekend, I was in bed, sick, but these fine folks made it out to the White Shell for a public event, and they said the turnout wasn't huge, but they did manage to get like 50 people out to do some observing. But the thing that made me really jealous was that apparently the seeing conditions were absolutely phenomenal, and I really missed out on some good views of Jupiter. So yeah, so typical RASC thing. I mean, they're all having fun. What else? I say that like I don't know. So every year we participate in the Manitoba School Science Symposium. We provide an award to the best astronomy project. Usually there's only a couple of them, but this year there was actually it was I don't know, this was cool. I didn't actually get to see it. Jade did the judging for it, but these girls did a project on the Northern Lights, and what I think is really impressive is they actually went out and did 7 nights of observing. They actually went outside, looked up, and did observations, which is great. It wasn't just like, I find a lot of astronomy projects, at school, science fairs and stuff, tend to be a lot of, I went and did research on the internet and I put it on a board, kind of thing, right? These girls went out and did observing. I think that's awesome. That's really cool. Apparently, Jay mentioned that they had a really interesting board on Aurora. Yeah, so. And they managed to get 2 nights of Aurora out of it. So very cool. The Sprucewood Star Party. So it is from September 6th to September 9th at Spruce Woods. This is a members and family only event, but registration's open, so get yourself signed up. If you have any questions, talk to myself, talk to Sylvia. Be happy to help you out. The open houses at the Lockhart Planetarium are continuing. The next one is June 27th at 7 p.m. Danielle's been running those. If you want to help her out at all, definitely reach out to me, reach out to her. And she's been doing talks and stuff like that recently. So. Telescope loans. Stan, how are we doing?
The solar scope's spoken for, but I have 2 loaner scopes available. The 2 8-inch stop zonings are available.
That's great. So if you are a member, we have 2 8-inch stop zonings available for you. It means you can only take one. You probably don't need both. Yeah, they're great little scopes. They're well taken care of. I know Stan does a fairly good job of keeping them.
I just put them through maintenance.
Keeping them in shape. Yep.
Collimated and ready to go.
Yep. So that's awesome. So yeah, if you're a member and you'd like to borrow a scope for a little while, I do recommend it. 8-inch jobs are super easy to use and super fast to set up. So you'll be observing in no time. If you need more club resources, we have our observatory. This is open to all members. You do need to get a key to the war room from Brian, although you could just go out there and use the pad. If you, again, have any questions, want more information on it, feel free to talk to me, feel free to talk to Brian. Members observing night. So I think right now, just due to the sun and just the situation with the sun right now, we're just gonna stay on hold for now, and then Brian will start them back up again once when things start getting a little bit darker. But this doesn't stop you from heading out there if you want to have a really late night. Totally fine by me. Not that I know. Okay. So this is something that one of our council members wanted to get going again. You should have seen a couple of emails floating around about it, and I think it also appeared in the latest Concentrics. It is the Explore the Universe program. This is a really good beginner's observing program. Not a lot of people actually go through and do it. I really recommend at least look at the list. There's some really good beginner objects in there, and it's actually just like if you're getting started and you don't know where to start, or if you've been out of it for a while and you don't know how to get back in, this will give you some goals. This will give you something concrete to go and try and do. So what we do is we take. We're actually going to, every month, we're going to take a few objects from that. So Dennis has basically picked some based on the list. And what we're going to do is I'm just going to suggest, based on Dennis's recommendations, some objects to look at. So, if you're going through the actual program itself, sketching is not required, but highly recommended. My sketches are, I will never show my sketches to anyone. They're terrible. But I do like to look back at them myself. It's kind of neat to go back and look at the stuff that you've done. So this time around, so for constellations, this month the focus will be on the constellation Vortex and the constellation Lemur. So fairly easy to find. For the moon, you'll want to try to observe the new moon on June 13th. Which is going to happen pretty quick. And then look for Mare in Imbrium and the crater Plato. So Mare Imbrium is right here, nice and obvious. And then this crater over here is the one that you should be looking for.
Brendan?
Yes?
Can I make a comment about the moon on June 13th?
Sure.
It's going to be, that morning, it's going to be 21 hours before the new moon.
Yes.
So it's a morning event.
Yep.
But it's one of those things, 21 hours is very challenging to try to see. It usually is only, a few degrees above the horizon before the sun comes up. Yeah. So, I'd recommend people who like to really go for a challenge. If there's a clear horizon, go for that one.
Yeah, it will be difficult because of the timing of it. So I would definitely, and so for anything that I'm recommending here, one thing to keep in, or anything in this list, you definitely want to go and do a little bit of research on your own, right? go through the steps of trying to figure out how to find these objects and what you need to do to be able to observe them. So, thanks, Dan. Yeah, and then just to round it out, for solar system, you've got Mars if you're willing to stay up for a while or just wait until it starts rising a little bit earlier. And then Venus, which is currently setting. This one you've probably already seen, but you know, make a note of it. Keep it in a log, right? Take a little sketch of it even. For deep sky object, M44, the VI cluster, visible with a pair of binoculars or a small telescope. And then there's a double star that you can look for, which is conveniently located in the constellation Botes. This is called M1 and M2. So those will be your targets for Explore the Universe this month. So feel free to give it a try. If you are going to be doing this, I would actually really like to hear about it. I think, or Dennis, like if you're interested in trying this out and you want a little bit of help, feel free to come talk to us. We will help you in any way. We've got lots of tips like the one that Stan just gave. So definitely want to get you involved and out there observing. So,
Brendan?
Yes.
Do they still require you to do this without any electronic help?
I think there's an option. Well, I know for the Messier one, there is a non-guided one. For the actual Explore the Universe one, I don't actually recall it. I have to check the PDF to see what it says. The information that you need is actually located right there. So if you go to rasc.ca/explore-universe, that'll give you there's actually a link to all the requirements and the description there. So my guess would be that I think it's probably an option, but for many of these things, you probably don't even necessarily need the electronic help. They're not most of the like even the deep sky objects are actually fairly easy to find with a little bit of experience looking at them.
You have to set up and operate the scope yourself, though.
Yes. Yes, definitely. Yes. So, yeah, but definitely, yeah. I can follow up on that too and clarify that for next month as well. So good stuff. Any other questions or anything like that? Do we have any other announcements? Did I miss anything? That was a lot. Sorry, I went longer than usual. Yeah, Dennis.
Still, if anybody wants to volunteer to come out and work with us on the Nature Conservancy next week, next Saturday, we'll be meeting down in Stewart, Berlin for 9 o'clock. Start time at 9 o'clock. I know it's before it gets dark, but there's a presentation to do, talking about dark skies and promote the concept to the local community. So if you're interested, contact myself, dennis.alliance.3@gmail.com. Thanks.
Thanks, Dennis. Yeah, the Nature Conservancy stuff is a really good thing we've been getting involved with. So definitely recommend. You got the time to help out. Yeah, and actually, if you're looking for some good dark skies, it's quite nice down there. Okay, we're gonna hand the floor over to Mr. Chris Gaynor, who's going to give us an update from National.
Great. Okay. Brendan was talking about the change in plans for this meeting. I think I bear a certain amount of responsibility myself. I live out in Victoria, and I'm on the board of the RASC National now. I'm the first vice president, handling things like publications and the Constitution Committee and things like that. But what happened was a couple of months ago, my wife approached me and said, well, my wife is a book editor and indexer. She said, well, the Indexers Conference is in Winnipeg in June, and I want to go to it, and do you want to come along? And I was looking for an excuse to get out of town, so I checked the dates to see, well, maybe I could come to the Winnipeg Center and have a visit. And it did turn out that everything kind of coincided, so I got in touch with Brendan and the other folks here, because this worked out for me, and it meant that I would come out here and pay the freight rather than the center or the RASC. We, as members of the board, we do try and get out to as many centers as we can. I think when our RASC was smaller, that duty used to fall on the president, but we're trying to get, it's just not possible for one person to do that anymore. So I thought this is a great opportunity. I wanted to come out to Winnipeg anyway because I enjoyed coming out here. And the last time I was here was for the GA a few years ago, and so here I am. And I'm just going to give you just a very brief presentation about what's going on at National. And I invite you to come up to me during the break or after the meeting, or even drop me a line if you have any thoughts on what you think we're doing, whether it's right or wrong or whatever. I just, sometimes the things that National does are not obvious to people. Of course, we know about the handbook and Sky News and RASC and various other things. The awards that Brendan was talking about, but we also take a lot of burden off the centers with things like the insurance. When you want to hold an activity, you don't have to run around and get insurance for it because you're already covered through National. There's also the thing where we handle a lot of the bureaucracy that comes with signing up members and things like that. And I must say, having served in the National thing, I am amazed at how much bother and work and spending there is involved in just running the National website. Not only a thing where we put up information, but we have our e-store and our membership renewal and service functions. It's just incredible how much work goes into that. I wanted to just share a little information about our financial information, our situation. Like everything, and I know you hear this tune all the time from politicians and various other organizations you're involved in, but it's always a challenge to keep costs down. We do make profits from things like the Observer's Handbook and things like that, but this can vary with currency fluctuations. For example, when the Canadian dollar goes down, that's usually good for the RASC's bottom line. A few years ago, we decided to purchase Sky News because it's become an important service for members, and we were concerned that it might be lost to members. We were hoping it would be a bit more of an income source than it has been, but we're we're still working on that. A couple of times we've had deficits. We've been able to cover them with investment money. You know, we once owned the national office, and what, 8 or 9 years ago we sold it because it was a big it was becoming a big problem. We had the office. We also had a tenant in there, and the tenant turned into the tenant from hell. And our folks in the national office were not that proficient in property management. So we sold it, and we do have this money there, and we have used it a couple of times to sort of get us through rough patches, but we can't really do that. And I think we're more interested in using that money for things that would benefit the really be a benefit for members. So here's a chart of sort of the spending we have for from the fees you get. And some of the things we do are paid for not by your fees, but through charitable contributions and income from things like the Observer's Handbook. So then there's of course the big question about dues. We increased them this year a small amount. The first time in 3 years. We were talking about increasing them more, and we still face that pressure. We're going to be discussing that at the next GA with the members of the National Council. So there still is pressure, and I'm afraid we will probably have some more dues increases in the coming years. But of course, we're kind of like you. We don't like paying more, and we're going to do what we can to keep a lid on it. You're probably also hearing from us about donations, and these are for special projects that are not member services. And yes, and we are also working on our strategic plan. The board, with input from the National Council, has been working on this for a couple of years, and these are some of the things we've done already. We still have some more work to do on that. You know, we did have our big restructuring kind of ordered by legislation that the government brought through a few years ago, and we're just trying to make sure with things like the strategic plan, it's not to have fun with strategic plans. It's just trying to get a bit more direction to our society operations and make sure they're what we do at the national level is of the maximum benefit to the members, and also to our goals of promoting astronomy with the public. And this year it's our 150th anniversary. We have some activities. The Imagining the Skies Astrophotography Contest. Check out that link I have up there. And if you've got some good astrophotographs, you should consider entering them in the contest. Our historical committee is putting out podcasts on the history of the RASC, We had the National Star Party in January, and I think we're having something else coming up in September. And we are also working on a new history book on the history of the RASC. And of course, we have the 2015 General Assembly in Calgary, which is, as always, going to be lots of fun. One speaker I'm really looking forward to is Emily Laktawalia, who's from the Planetary Society. Does an excellent blog on planetary exploration. And she talks a lot. I actually saw her speaking in my Hubble travels about amateur astronomers processing imagery from NASA. There's a lot of that going on, and she's the expert on it. So I'm really looking forward to her talk at the GA. And so that's basically what I have to say. And please don't hesitate to let me know what you think, even if it's critical, because we're just trying to do the best job we can. We started out as members just like you. Most of us have been through center executives. You know, a number of years ago, I was in the Victoria Center executive, and I'm looking forward in a couple of years to just going back to being a regular member of the RASC after my tour at National is over with. So that's all I have to say for now, and I'll be back after the break, I think.
Cool. Thanks, Chris.
Thank you.
Next up, we'll have Jay giving us a Lost in Space, which was we started, we've done one of them a few months back, and it was an idea that Jay had to give us a tour of, well, not a tour, but a focus on a spacecraft that we probably haven't heard from in a while floating around. Likely something that Emily Laktawalia knows all about. By the way, I totally agree with Chris. If you have not read her blog and you're interested in space exploration, you're missing out. So check out the Planetary Society. I highly recommend her blog. It's phenomenal. Take it away, Jim.
Lost in space. Here we go, part 2. Satellites you never heard of that are still operating. Spectre. Nice name too, but it's also called Radio Astron. It's a Russian satellite. It was launched in 2011. Had a little problem in front because, as you can see from this image, it's quite a large antenna on it. It wouldn't deploy at first until they pointed it at the sun for a day and warmed it up, and then managed to open it up. Seems to be a common problem. The interesting thing about this satellite is its orbit, which you see is quite an elliptical one, from 10,000 to 350,000 kilometers in distance from the Earth. Last year, the way they designed the orbit on this thing is that it would eventually get into a position where it would be an eclipse from the Earth. It wouldn't be able to get power to its solar cells for a long enough period that it would go out of control. So they made a critical orbital correction last year to keep it going. I think it might have been a little surprised that it was lasting as long as it did, so they adjusted the orbit so it can only tolerate about a half hour outside of or in the shadow of the Earth before it starts to run out of juice. The operating wavelengths are relatively long, all the way from 1.3 centimeters down to 92. But as a consequence of its orbit and the way it's operated, it has a resolution that's pretty phenomenal, 1/10,000th of an arc second, which means that the detail that it can see is extremely fine. So how does it do that? Well, its science goals are really to take a look at the high energy processes. Those are what the wavelengths that it's looking at are most suited for. And particularly wants to look at what's happening in the cores of galaxies where they have black holes that are very, very energetic. There's a lot of mystery on just what the black holes are or what the observations are showing of the black holes. How do those jets get generated? We saw a picture of one of them from Brendan's talk earlier. And just what is the energy processes that winds them up? Well, it's made a lot of discoveries in the 7 years it's been in orbit. And most of these don't look very dramatic when you look at the images like we see here. They're just the usual colored blobs that are so common in all of X-ray and gamma ray and radio observation. Nice and pretty, like, oh, should I let it do this? Oh, it didn't pop up. It just told me that important updates are available. Anyway, 27 microarc seconds here at the 3C273. A lot of you will know that name. That was one of the first quasars that was ever discovered. Quasar, a very active core of a galaxy. So they have a resolution of about 2.7 light months, which doesn't seem a very fine resolution, but 3C273 is an awfully long way away. What they found was the temperature of the outflow is a little bit higher than they expected. 40 trillion degrees. I'm not even sure the word 40 trillion degrees even means anything. 10 to the 13th certainly does mean something. But it's a little warmer than the 100 billion they expected. It's not supposed to be possible to get to that high a temperature because the electrons interact with each other once the temperatures get very, very high, and that serves to cool them off so that the temperature is constrained. The other thing they found is that looking at this with the extremely high resolution they have, they could see essentially twinkling of the radar signal as it passed through the tenuous gas in our Milky Way, the same way you see twinkling of stars with the light of the star passing through our atmosphere. And from that they were actually able to derive some very nice constraints on the density of material in our galaxy, especially a long way out from the center where it's particularly difficult for us to observe. Well, that's not supposed to be the end of the slideshow. What happened here? Four, there should be 15 of them there. Try reloading. Maybe we can put that one in. Always carry it back up. Close that. There we go. Put me up. All right. Well, for some reason, one of them didn't. So anyway, go back to the science goal. High resolution to galaxies, observation of stellar nurseries, places where stars are being formed, Brendan talked about. Pulsars and neutron stars, really, really compact objects that need a lot of high resolution. And they also wanted to see if they could find the gravitational redshift of the Earth, which seemed like a little bit of an interesting problem, but would be amenable to looking at wavelengths with high resolution. So we've been through here. 3C273, this is a picture of it, and you can see up to the side there in the upper left is a little streak, and that's actually a jet that's coming out of 3C273. The galaxy itself is 2 billion light years away. I put 2 billion years, but it's actually a little, has to be light years. And it's quite a heavy little object, but its size is very tiny. Now this is that is the size of the central energy generating mechanism. but it does lie in the center of a large elliptical galaxy, so it requires a lot of resolution to be able to see it. If we take a look at this image from Hubble, or from Chandra and Hubble, you can see that the highly magnified view of this jet. And you see X-ray energy in blue, which is the most energetic part of it. You see the visible light energy in these colors around green, and you see infrared energy here. And what this is showing you is that the core of 3C273 is way back here somewhere off in the middle of Winnipeg. But this, the energy in this jet fades away from ultraviolet and X-ray on the blue end into infrared and even into radio wavelengths on the far end. So what Spectre was trying to do is actually resolve the very, very core of that thing. And that little dot that was at one end of the previous in here is actually resolved into these kind of contour fields that you see here. And they're able to follow over a period of years these things moving outward at significant fractions of the speed of light. And they can also see new components such as this one here forming over in 2-month intervals. So the resolution is high enough to actually see activity in the very core of that jet. Of course, then you have to go through the mathematics to explain what's happening. But they did see that there was a very strong flare just before, by several months, this new ejection started up with the energy flowing out of the central object. Another core of a galaxy is Perseus A. You can read all of this in here. The black hole that's generating this jet is up in here. What's surprising is that the jet is so wide. They would have expected it to be a very, very much narrower jet than that. You see we have 0.3 of a light year signal here. But the central resolution, the resolution of some of these tiny little bits here, is of the order of our solar system. So what we're seeing here is because this is a very wide jet, the explanation is that it doesn't actually start at the black hole itself, which is a tiny little object, but instead in the debris field that's circulating around the black hole, which is a much wider surface area. The other thing I wanted to look at was masers and lasers. A little explanation here. This little laser here has actually got a battery that elevates the electron in the crystal here up to a higher energy level. And in a galaxy, it's like this. You get something that causes an electron to go from its ground state, its rest state, into an elevated orbit, if you will. And there are fixed levels here. Well, that represents a certain amount of energy, which also represents a certain wavelength of light. So while these electrons are pumped up into this excited level, something we call a population inversion, it waits for a wavelength of just the right energy to come by that's equal to the energy here. And when this wavelength passes, this sort of says, hey, I'm going to go along with you. It falls back and it generates its own wavelength that goes along with this one. If you get a whole bunch of them cascading, then you end up with something like a laser where a beam of light is coming out with a whole bunch of wavelengths all at exactly the same energy. These things in a nebula, something like that, are excited by usually ultraviolet radiation from a star, and so you end up with certain molecules elevated to a certain energy level, and when a wavelength of the right wavelength comes by, you suddenly get emission, a strong emission, just like a laser, of energy. And it looks like a tremendously hot object, just like the amount of light coming out of this laser, would, if it was an incandescent beam, would have to be somewhat hotter than it actually is in my hand. But it's not really that, it's the fact that it's got this stimulated emission. So maser is simply microwave amplification, laser is light amplification. So anyway, they're looking at the Elephant Trunk Nebula in here. They found 30 masers inside that thing. And those masers seem to be clustered into groups. And those groups, actually, they find certain characteristics. Now, the light source of this, they all seem to be illuminated by the same source, which is a star with a lot of ultraviolet radiation. a highly variable intensity, and they have various different speeds. So basically what you're doing is you're mapping out tiny little areas that are less than 3/100th of an astronomical unit in size. In other words, about 1/30th of the distance from the Earth to the Sun. So it's extremely high resolution that's possible with this thing. What it seems to be is there's a star, very hot star, surrounded by dust and gas. Can't really see it, but the ultraviolet light shining out through the openings or the poles of this thing where there is no dust and gas are striking gases on the edge of the nebula and creating masers in these places where they're creating this population inversion from the gases there. BL Lacerda is another one, also a band or an orchestra, but that's AGN is an active galactic nebula or nucleus. So again, we're looking at high energy processes. And depending on which way you look at these things, if you're looking at them from the edge, all you see is the jets coming out the sides because the dust and gas here stops you from seeing into it. And if you look at them from end, we call these Seyfert ones and BL-LAC objects. And with that one, they have an enormous amount of resolution. So you can see from this little video, or little movie, that Radiostron depends on hooking up with Earth-based observatories and its own position in space to create a virtual telescope the size of the distance between the two of them. So its observations are equivalent, at least in resolution, to having a telescope that's 35,000 kilometers across. And that's why it's able to get that kind of high resolution. So there's some talk about having a follow-up that would have an even more distant orbit to get even better resolution. There are a number of other smaller, similar telescopes that other countries have, but this is by far the biggest. And the problem is the Russians don't really have the money to follow up with that right now, so they're looking for other nations to help out with them. So you get a higher resolution if you go with smaller wavelengths, but you have to realize is that in order to make these multiple telescopes work, you have to know their position relative to each other to within a fraction of the wavelength that they're operating at. So if you're operating at 1.9 centimeters, you have to know where that spacecraft is to the order of a few millimeters compared to the position of the radio telescopes you're using on Earth. Well, thank you very much. That's Lost in Space for this time.
Okay, Brian will be up next with What's Up?
Short time, we'll get this brief then. Okay, so We'll talk about a little bit about June, what's up in the night sky, and I'll touch a little bit on July too, because next meeting will be at barbecue. And there's a reason why I want to talk about July, because my favorite planet is coming up, Mars. So let's talk first about the planets. We'll start off with Mercury. Move on right next. Okay, so not much for Mercury. It's well, pretty much right now it's going to be a day planet, and eventually we'll move on to an evening planet. Venus, well, it's early twilight, but still visible. So on, what's it? Is it on the 11th? No, the 1st. It's like 2 degrees from the moon. Mars, I'll talk a little bit more about Mars. Again, it's my favorite planet. Of course, the closest approach is on July 31st, and it's going to be roughly about 24 arcs across. Jupiter, well, the opposition happened a couple of weeks ago. Since we mentioned about that public event at Whiteshell, that was probably one of the best viewings I got for Jupiter, thanks to Tim. Okay, Saturn, its opposition would happen this month here on the 27th, and of course it's only 2 degrees from the moon on the 28th, so that'll be interesting to see. All right, here's an overview of the planets. So we just passed Jupiter, we're approaching Saturn, and of course Mars on the 31st. Mercury is still pretty close to the Sun, and there's Venus. Okay, if I had members night tomorrow night, I was going to show the planets. Of course, we have Jupiter over here, this is Saturn, and this is Mars. So this is on the 10th, or roughly about 3 o'clock in the morning. It's kind of nice to have all 3 planets at once. I did spend a couple nights this week viewing some of them, Saturn. Of course, it's pretty tough to stay up and work the next day. All right, June. Not much really happening for June. Someone says a supermoon on June 28th, according to one article. July. Okay, we do have a meteor shower on the 28th, but we have the full moon to compete, so that's kind of not going to happen. And of course, we do have Mars, like I said, approaching at the closest point. What's so neat about Mars is that it's every 2 years. I'll explain a little bit more about later. We have the meteor shower again, of course. We have the full moon to compete. So that's not going to happen, so I'm not going to do any special events on that. Okay, Mars. What's so special about Mars? Well, the viewing happens every couple years. 2, I love the surface details. One of the challenging aspects of Mars is viewing. On my 12-inch, that polar cap just comes out really blue. We've got this really nice bright surface to look at. It varies in sizes every 2 years. And this year, it's going to be not the biggest, but it's going to be 24 arcs across. And it's going to happen really soon, next month on July 31st. But in 2020, it's going to drop down in size. So here's Mars right here. This is the orbit, and this is it only goes up to 2018. So the smallest happened around 2012. Back in 2003, it was about 25 arcs across, so that's the biggest. I heard it was pretty good. A lot of people with even 4-inch telescopes were able to see this. Okay, this is this year. So in May, is that small? I'd say roughly, 13 arcs, and this is going to be 24 arcs across. So it's going to be really big. I think it's spectacular, but unfortunately, it's going to be kind of low in the sky. But we'll see how it happens. I think it's pretty high enough to view it. There's other times where I know it's a little higher, but it's in the winter time. The next viewing is going to happen October the 6th, I believe. 2020 is the date set for it. But it only going to drop a little. Here's a little catalog or a chart I put together. Okay, this is the year. So it's going to drop down to about 13. There's 13 up here in 2012. And so 20 drops to 22, 17, and 14. So just to bear in mind, so next month would be a really good chance to view it. If you don't, unfortunately, I think some people are moving. I don't know. I think some people are heading south more, so they'll have a better viewing because it'll be higher up in the sky. So yeah, I'm really, really excited about Mars coming up. And I think that's it. I promised someone, Dennis, Darren, sorry, right, you're here, right?
Yes, right here.
All right, so he wants me to make an announcement today Well, he donated some filters, right, to Glen Lee. It's already there. So the next observing night that we have probably in August, we'll talk a little bit, well, I'll show you some of the filters. We also have that 6-inch that I haven't really put up yet, that Stan has given before. So it'd be nice. But unfortunately, because of summertime and the sky and all that will be terribly dark, so we won't have any observing nights this month or next month. But at the barbecue, we'll probably have some telescopes for you guys viewing. Of course, we'll have the LX200 going, just in case. All right, so that's all I want to say. Thanks, Darren.
Okay, now's the part of the show where Ian gets his back set up, and I entertain you for about a minute or so. I was actually, I was working at the York University Observatory during Mars's closest approach in my first year of university in 2003. That takes me back. We had, I don't remember what the exact count was. This was in Toronto, and it was thousands of people. Thousands. It was one of the most overwhelming things I think I'd experienced at that point. People were literally getting maybe about 5 seconds at the eyepiece to look at Mars when it was at its closest approach. So, yeah.
Brendan?
Yes?
We did something as well at Birds Hill Park.
Yep.
And they estimated we had between 3,000 and 5,000 people show up at Birds Hill Park.
Yeah,
To do the
that's...
same. So I think we had, what, about 50? Jay, are you paying attention? No. How many scopes do we have out at Birds Hill Park? About 15 for the Mars observation? So,
Yeah. So we'll see what we're going to be doing this time around. I don't anticipate it getting the same media attention that it did last time, but hey, you never know. And as Brian said, it will be a bit of a challenge, but we'll talk about it, and if anything comes up, we'll certainly let everyone in the club know what's going on. The one thing I did want to mention briefly, I sent an email out about this just before the meeting. I forgot to get us a reservation at the normal Boston Pizza that we go to, and they've got a group of 50 coming in tonight, so I had to change plans, and we will be at the Boston Pizza on Taylor. So not Pembina, but Taylor. I do apologize for that.
Taylor and...
It's Taylor, it's south of Grand Park Mall. It's Taylor and... Nathaniel, thank you. So it's Taylor and Nathaniel. Right by the Sobeys. Yeah. There's also a Starbucks in there, but there's a Starbucks everywhere. Yeah, just go near the Starbucks. Okay, you're all good?
Or well, we're as good as it's going to get.
Okay.
Good as,
So Ian will be providing us with an update on what is new in the science of astronomy.
speed news, right?
Speedy news, you're okay. I never heard of that.
All right. Turns out I've got 4 short articles for you. It's thought that maybe there wasn't a lot going on in astronomy this past month, and it's because all the astronomers are going to conferences these days, you know, so they'll get it all. Okay, first little bit of news. You may have heard about this, okay? Brings us back to the Catalina Sky Survey telescopes and the work they've been doing. Of course, you know that what they do is they look for near-Earth objects. All right? And 2 of the telescopes for the survey are actually on here. They're off to the side here. A 1-meter telescope and a 1.5-meter telescope. The other telescope is mounted on a mountain nearby. Okay, so what did they find? If you look at this and you don't blink, you should see something moving across the screen. And for those of you who need a little bit of help, oh, is that not working? That's a nuisance. All right, let's get. I'm not sure I did. Okay. Well, okay, you get to see the individual frames. And so these are the discovery photographs of asteroid 2018 LA. It was first detected at the orbit of the moon. 8 hours later, it was entering the Earth's atmosphere at 17 kilometers per second. And it turned out, this tells you something about the efficiency of this program for detection. This actually, NASA wasn't worried about this telescope. No, it was only a few meters across. And so it was going to disintegrate in the atmosphere. So at that point, there's no further alerts issued. But you managed to plot the trajectory across the globe here, okay, and it turned out that there were enough observations, and it turned out the trajectory was reasonably placed. Somebody had a webcam handy, and if you look in the top, let's see, right, always have problems with this, okay, right section, okay, for a few minutes, okay, you'll see that it got caught on kind of impressive, all right, so a little bit of serendipity there. Somebody had, well, this says cam number 2 on there, so I guess you guys are here to see that. All right. A while back, okay, we were having a look at gravitational wave detection, and one of the last one, basically a kilonova, think supernova, all right? And so basically a merger of 2 neutron stars. The sort of open question was, do we end up with a more massive neutron star, or do we end up with a black hole? Well, it turns out that the jury is in, or at least there's some convincing arguments, okay, to suggest, in fact, that we have a black hole. And the sound doesn't work for this, as sort of as expected, so we'll just hold on. The interesting thing about this is that the thought is we do in fact have a black hole forming. Let's see if I can do that. And I'll try this again. Okay, but the interesting thing is it's probably now the smallest black hole that people sort of have actually found. And with a little bit of luck, if I keep my fingers away from the iPad, we should be able to follow this through. Basically, it's the follow-up observations from after the gravitational wave detection. You look to see what's happening, you look for the presence of X-rays, and you find that you can actually rule out the formation of a massive neutron star. And they put together a nice little summary of this, what the thinking is. All right, so you had a spoiler from the last time. Okay. There's some interesting work now being done on the possibility of searching for habitable exomoons. The normal thought, of course, is to go for planets. All right, and we know in our own solar system, okay, that we've got lots of moons. And some of these moons are rather interesting. Right? And so basically following along that line of thought, if we have a look at ocean worlds in our solar system, basically these are all outside the habitable zone. In other words, we don't really expect to find something there necessarily. Okay, but there is tidal heating in the interior. We have some very interesting things happening. If on the other hand you have a look at extra solar planetary systems, you actually have larger planets and the possibility of moons which sit in the habitable zone as well. So not only are you in the habitable zone, but you are also have some benefits being close to a massive parent body and interior heat. The thought behind our own, if you like, ocean worlds, farther out, is you have some tidal heating, you have possibility of hydrothermal events, and of course we witnessed water and ice case geysers up there. There's one small problem that one paper has pointed out, is that do you actually have enough of the chemicals that you need to support life? And of course that again is an open question. Their simulations seem to suggest that it won't happen, all right? But it still is an exploration worth considering. Okay, either, it's a nice thing about it is you get a positive result or a negative result, and you get to check on your thinking. Picture of the month. And you may recognize this one. Okay. No chorus. It's a Megacentauri. Okay, it's a Spitzer photograph. And in some ways, I basically just wanted to show you a globular cluster. So, and I may have chosen inadvertently one that is kind of interesting. The caption that reads with this one is that this, in fact, may be somewhat anomalous, in that there's a suggestion that the population within this particular cluster of stars doesn't quite fit. The study of globular clusters is important for us because we think they're amongst the oldest objects we have around in the universe. And typically you put ages around about 12 or 13 billion years. And it turns out that current studies, current models, make them 4 billion years younger. All right? And so, since your normal models for forming galaxies and all that, we've got 100, 200 globular clusters floating around the Milky Way, is that it does have some impact on our understanding of, if you like, the earlier history of the universe and the formation of galaxies. So, hopefully that's short and sweet enough that you can get on with the break.
Wasn't that short? Wasn't that sweet? It was just right. Yeah, so we take our intermission, aka refreshment break. Okay, not sure that everyone has quite made it back yet, but we should get going. So I think for quite a few of you, the space event that you remember was, as a child, was men landing on the moon. Not to date too many people in here, but I got a sense that might be working. For a young Brendan, staying up late watching the repairs to the Hubble Space Telescope was mine. It's actually one of the very early memories that I have of hanging out with my dad, which should tell you something about the relationship that I have with my dad. There was a lot of nerdy stuff in there. Yeah, so that was the real thing for me though. Like watching that repair was really cool. Now at the time I didn't understand what that was for or what it was about. I just thought it was cool that we had a bunch of people in space doing work on something or other. But as I got older and learned about what the Hubble Space Telescope was, and I continued to follow along with those repairs, those subsequent repair and enhancement missions, I mean, like all of us, I fell in love with it. So when Chris reached out about possibly doing a talk on some subjects, and I saw the HSD in there and the history of it, I was like, yes, please. That sounds great. So, tell you a little bit about Chris. He's a historian specializing history of spaceflight and aeronautics. He has 4 published books and is currently writing a history of the Hubble Space Telescope for NASA. And as you heard, he's also the first vice president of the RASC. So, if you could join me in welcoming Chris Gaynor.
Thanks very much, Brendan, and thanks for your earlier talk. I think it'll allow me to get through this one a little quicker. Yeah, I'll tell you a little bit about my part in this story. I've done various things in my life. I've been a member of RASC for a long time, and I've always been interested in space exploration. Of course, I remember Apollo 11 like it was yesterday, and I'm still wrapping my mind around the idea that we're soon going to be celebrating the 50th anniversary of that event. Something I've thought about between Apollo 11 and Hubble is that, of course, Apollo 11 was a huge television event. You know, Walter Cronkite and the whole thing, the moonwalk on television. And I've kind of thought of Hubble as being almost the equivalent for the internet age of Apollo and television. And I've actually even, in the book I'm working on, I've written about Hubble's relationship to the internet, and also, published an article about that already in a journal I'm involved with called Quest, the History of Spaceflight Quarterly. So there's all sorts of interesting things to do with the Hubble story. But I've done other things in my life. I was a newspaper reporter. I was in communications for the government out in DC. I got caught in a change of government and decided, well, I always wanted to be a historian, actually. So I went back to school and got my PhD in history. And I'd already started writing books about the history of spaceflight. I wrote a book about the Canadians who worked on the Apollo 11. Most of them after they lost their jobs on the Avro Arrow. So that kind of got my Apollo 11 book out of my system. And then I subsequently got my PhD in history, and I studied under a fellow named Robert Smith at the University of Alberta. Before he was at the U of A, he was at Johns Hopkins and wrote a great book on how Hubble was built called the Space Telescope. It's still considered almost a masterpiece in the field. But that book was written before Hubble was launched, although you can get a paperback edition which has a little bit about what happened when it was launched. And a couple of years ago, some folks in the Hubble project at NASA Goddard Space Flight Center decided that it was time that another history of Hubble be written, mainly about Hubble operations. So they had a competition amongst various historians, and yours truly was chosen. So I spent the last 3 years immersing myself in the world of Hubble, and written a draft of a book, and we're waiting for some decisions about publications, and then it will move to publication. There'll be probably another draft I will write, and then it should be published. And I'll certainly, I would imagine there will be some publicity when the book comes out. Anyway, I'm going to share some of my findings with you now. I'd like to thank Brendan for his oh, is there a problem? For his introduction, and you know, I too I too got up late to watch those EVAs during the first servicing mission in 1993. I didn't do them with my father, but I'm glad to say he's still around, but he wasn't that dedicated to watching Hubble. One thing I did is, being a bit of a pack rat, I taped a lot of those spacewalks, so I was able to put those tapes to use when I was working on this book. So occasionally that junk you collect and put aside is of use. So, but let's get into the meat of the talk. So, of course, the Hubble telescope is named after Edwin Hubble, and Brendan was talking a little bit about some of the work he did with helping us determine that the universe was more than just the Milky Way. His work with the Andromeda Galaxy, and seeing as this space telescope was going to be kind of following in his footsteps in determining the dimensions of the universe, I think his name was kind of a natural one to put on the telescope. Lyman Spitzer, who was an astronomer at Princeton, is considered by most to be kind of the quote-unquote father of the Hubble telescope. He wrote the first kind of detailed proposal for a space telescope in 1946. It wasn't, I think the idea had come up earlier. Hermann Oppert talked about it in the 1920s. But Spitzer wrote about it in 1946, and then in the intervening years, the years that followed, spent a lot of time promoting the idea. And it's actually quite interesting to observe that not every astronomer was immediately keen on the idea, and a lot of that history is covered in Robert Smith's book. Spitzer did live long enough to see this space telescope launched, and he conducted observations and was quite an influential voice in the running of the Hubble telescope while he was still alive. Now, of course, as Jay's talk kind of suggested, Hubble is far from being the only game in town when it comes to space astronomy. And it was by no means the first one. We had the orbiting astronomical observatories starting, I think they launched one in 1966 and it flamed out, but the second one worked. Those early telescopes were not all that big, and of course have limited capabilities, particularly in terms of getting images that some of us in the public might be interested in. Probably to this audience, I don't need to spend a lot of time on this slide. I think everybody here is familiar with the impact of the atmosphere on our observations and why we want to get above it. And then, of course, there's the matter of the various wavelengths that we want to observe it. And this slide shows the great, so-called great observatories from NASA, the Compton Gamma Ray Observatory, the Chandra X-ray Telescope, Hubble, and the infrared telescope that's named after Spitzer. But there's all sorts of other telescopes, including the one that Jay was talking about. So this is kind of a cutaway of Hubble, and you can see it's a Ritchie Craighead telescope. I think about 94 inches across, if my memory serves me right, or thereabouts. The main mirror is here, and then secondary mirrors here, and the light goes into these instruments back here. So right below the mirror, there's 4 instruments that kind of look like baby grand pianos. Now, one of them is a camera, and the other 3 are the fine guidance sensors. And then below them are 4 other instruments that are kind of shaped like phone booths. And these instruments were designed to be changed out by astronauts from the shuttle. This, of course, is a very important part of the whole Hubble story, is that it was designed to work as part of the space shuttle system. Without the shuttle, the story of Hubble would be different in so many ways. I don't think I could count them. But over the history of Hubble, we've had all sorts of different instruments that have flown on board Hubble, and so a lot of the work I was doing was going into the history of each instrument and why they were put in and why they were, in some cases, taken out, and some of the horse trading that was going on amongst astronomers in that process. Some of this has to do with the servicing missions, and you can see a couple of these instruments. I think that's the wide field camera 3 there, and this is astronauts changing out one of the other instruments during the servicing mission. So HST is more than just the spacecraft in orbit. It's about the size of a school bus, and it can keep in regular contact with the Earth thanks to these tracking and data relay satellites, TDRS, which began to fly in the 1980s. This shuttle deployed the first generation of these things, and more recently they've been deployed by regular rockets. And TDRS is used for all sorts of payloads, many of them scientific, some of them national security. It's used for the International Space Station. They replace those tracking stations from the old days that some of us might remember from the early days of the space program. So HST uplinks and downlinks go by TDRS. They originate at the Goddard Space Flight Center in Greenbelt, Maryland, which is not as well known as some of the other NASA centers, but it's really an important one because a lot of the scientific payloads that NASA launches are controlled and designed and all this at Goddard. When Hubble was built, it was actually the construction of Hubble was actually done by the Marshall Space Flight Center in Alabama, which had previously done the rockets. And anyway, that's a whole other history that I don't really touch on because Goddard essentially took over once Hubble was launched. A big issue when Hubble was being organized before its launch was what were the roles of the scientists going to be in Hubble, and Goddard, I think, naturally assumed that they were going to just be controlling it with their own scientists. But there are a lot of astronomers who didn't feel comfortable with NASA having that much power, and so through various bodies like the National Research Council, they advocated, and so this institute was set up after a competitive process in Baltimore, and it's roughly about a half-hour drive, maybe a bit more, from Goddard, and so the scientific operations for Hubble are run out of the Space Telescope Science Institute, and you'll see most of the announcements for Hubble are jointly done with STSCI and NASA. Now, STSCI is part of AURA, the Association of United Research Institutes. I forget. I've just forgotten the acronym. But it operates a lot of astronomical facilities such as Kitt Peak and Gemini telescopes and things like that. Hubble is also a program of the European Space Agency, and ESA provided one of the cameras, the paint object camera that was in the original set on Hubble. It supplied the first 2 sets of solar panels. There have been 3 sets, and also a certain proportion of the people who work at the institute. Canada is not a formal partner in Hubble. Although, you know, we are a partner in the James Webb Space Telescope, which I'll talk about a little later on. But there are 3 places on Earth where there's a complete set of Hubble data. One of them is the Institute in Baltimore. The other one is ESA. I think they have an archive in Spain. And the third place is just down the road from my place at the Dominion Astrophysical Observatory in Victoria. And that happened because Hubble is kind of an early example of big data coming to astronomy. And when the Institute and NASA were setting up the original archive for Hubble, you know, they were having some problems, and the Europeans helped them deal with those issues. And Canada had set up the Canadian Astronomy Data Center at the Dominion Astrophysical Observatory because we wanted to have access through our own sources to Hubble data. Now, of course, this is in the pre-internet days, so it was kind of a different mindset back then. But it turned out that the folks in Victoria were able to help establish the data setup for Hubble. So I have to talk about some of the background of how Hubble was built, which we'll talk about in the next slide a little bit. But officially, my book starts on this date when Hubble was launched, and it got off to a good start, and everybody was quite excited. it had been postponed several times, and including when the Challenger blew up in 1986. That actually, I've come to the conclusion that, you know, of course, that was a horrible thing with the loss of life, but one of the hard-won benefits out of that was that they had more time to prepare Hubble for flight. I'm not sure what would have happened if it had, say, launched on schedule in 1986, because there was a number of other issues that they were still trying to iron out, including control issues. They had a lot of problems with the solar panels. They had enough problems with the solar panels as it was when they did deploy it, but there were even worse ones if they did deploy it in 1986. So that time was put to good use to make Hubble better, but they missed something. The main mirror was grounded precisely to the wrong shape, and so of course I get into that issue a lot. How did that happen? That $1.5 billion blunder. Now, the mirror for Hubble was precision grounded at Perkin-Elmer about 1981, long before 1981, long before Hubble was launched. That happened at a time when the program was under a lot of stress, managerial stress, financial stress, and basically the contractor decided that they could cut corners on a test, and they should have done, as a matter of course, ordered, had another test done, kind of separate from the main testing of the mirror, but they didn't. And in setting up the main testing rig for that mirror, something didn't sit quite right, and they decided to throw in like a 30-cent washer, and so that was how they wound up grinding the mirror to the wrong shape. There was a backup mirror that was done by Eastman Kodak, which was ground to the right shape. And if you're in Washington and drop by the National Air and Space Museum, you can see that mirror. Anyway, it was it's a very complicated tale, as these things tend to be, and it came at a very difficult moment for NASA, because even though they kind of recovered in a sense from the Challenger accident, they were running into other problems, like for example a stuck antenna on Galileo, the Mars observer. There was various other problems, and so the story of how they dealt with this is really a great story, because people were just kind of poleaxed that this had happened. How could this happen? But both scientists at the Institute and at NASA, and also at the Jet Propulsion Laboratory, went to work on devising quite an ingenious solution to this problem. And of course, that led to the famous Servicing Mission 1 in December of 1993. And what they decided to do was, first they pulled out the original camera on it, the wide field planetary camera. And a guy named Ed Weiler, who was an astronomer and kind of a high figure at NASA, fortunately asked to start working on the WIFPIX replacement long before Hubble was even launched. And so they were able to make some changes to the replacement by incorporating lenses in there that compensated for the spherical aberration in the mirror. But then you had all these other instruments on board. How do you deal with them? Because you can only replace so many instruments in a mission, and some folks, under the direction of scientists at the Institute, came up with an idea which was called CoStar. One instrument had to be sacrificed. The high-speed photometer was removed, and CoStar was put in, and it was basically kind of a set of contact lenses for the other instruments. The instrument was put in, and then after the astronauts left, these mirrors, which are about as big as quarters, were put into the line of sight of the optical channels and changed the shape of the light so that it hit the instruments as originally intended. And the whole thing worked, thanks in part to the astronauts, but just some amazing optical work done by folks at NASA and various private sector places that specialized in high-performance optics. So it was an amazing story. But if that mission had not been pulled off, I'm not sure. I'm not sure whether we would still have NASA in its current form, because it was very critical, and NASA had gone through a bad stretch. So anyway, over Christmas, they started to test the telescope, and it was almost it was working virtually as well as anybody could have hoped. And very quickly, Hubble is this symbol of failure, disappeared to become a great symbol of American success. I don't know if you remember Naked Gun 2.5, or one of those Naked Gun movies, and there was a scene where they go into a bar, and all the decor is various disasters like the Hindenburg and the Challenger and all this stuff, and Hubble. And now that quickly was forgotten. Shortly after Hubble was fixed, of course, we had Comet Shoemaker-Levy 9, and the first images of the impacts came from Hubble. So there have been 5 servicing missions. The first one we talked about, and then there was 4 after that, and each one of them kind of has a different story, and I can't really get into all of those stories, but they'll all be in the book. Certainly a notable one is the last one, which took place 9 years ago now, more than 9 years ago, and a lot of the problems, for example, with the gyroscopes in the earlier servicing missions, those fixes only worked for 3 or 4 years. But the fixes that have been affected in this last one, particularly with the gyros, they had some better I would really be getting deep into it to explain the differences, but anyway, they have better gyros than this last one. And Hubble has 6 gyroscopes on board, which are used to aim it rather than thrusters. And 2 of them are no longer operational, but after 9 years, I think that's amazing. So, most of the instruments on Hubble now are kind of 3rd generation instruments from the ones that were used here. And these instruments are a lot more powerful than the ones that were installed when it was first flown. So this is an important part of the Hubble story, because usually you launch something and that's what you've got. And Hubble is kind of a different spacecraft now than when it was launched. A number of the repairs that were carried out in some of these missions were repairs that were never even contemplated when Hubble was launched, and it took really amazing ingenuity and dedication to figure out how to fix some of these programs, like computers failing and changing out solar arrays and things like that. That's a big part of the story. So Hubble, one of the things that sets Hubble apart from many other in-space telescopes is, of course, it operates in optical wavelengths and as well as other wavelengths, and is this legacy of amazing images, which the public has been interested in, and is part of the story about Hubble and the internet, which I won't get into here. Because Hubble works in several different wavelengths, when folks involved with the Public Affairs Office at the Institute were preparing images for release to the public, they couldn't process them the same as one would if you were working only in optical wavelengths. So they had to deal with make some judgment calls about how they process these images, and that's kind of an interesting part of the story. For example, people like Ray Ballard and Zolt LeVay, who do a lot of this processing for public release, they've written about what wavelengths they've chosen when they've written articles in places like Sky and Telescope, and because a lot of astronomers, amateur folks, are interested in the work they do, and it's been very influential because Hubble was working with CCDs while most of us were still hypering film and doing stuff like that. But of course, CCDs soon fell into our hands, and we've had to make some decisions about how we process those images. And so I've written a lot about that. There's a lot of interesting questions to explore. You know, like what is reality? You know, what is the reality? And especially when you consider that what our eyes can see are kind of limited, and you know, even the images that we've always processed with telescopes are different from what our eyes see. It's quite an interesting question. So Hubble's scientific work, of course, it's a huge it's a huge, huge topic. And I've tried to just, you know, even at some length, I think what I've been able to do is only scratch the surface. And the thing is that even if Hubble conked out tomorrow morning, there's still a lot of research being done, because a lot of its data has never been looked at. It's just gone into the archive. And so there's going to be a lot of work done on it. The other matter is that, of course, there's all sorts of other telescopes working on a lot of these questions, including space telescopes and telescopes on Earth. You know, I talk about the work on the Hubble constant and the size and age of the universe, and a lot of these projects involve numerous telescopes, and Hubble is only part of the story. So it sometimes gets a little complicated in figuring out, well, where does Hubble's contribution end and these other observatories begin. But these are some of the highlights. Of course, with things like extrasolar planets, because of Hubble's great power, it has a very narrow field, so it's not very useful for survey type work, but it can be called in to do detailed observations on objects of interest, such as some extrasolar planets. And this is actually, this slide kind of covers some of the issues that Brendan was talking about earlier on. Just the difficulties of figuring out, well, you know, how far away is that star? How far is that galaxy from us? And the use of Cepheid variables in certain types of supernovae. So I'm not going to go into that. Arguably, one of the most important images that Hubble took, and certainly one of the great stories of Hubble, is the Hubble Deep Field, the original Hubble Deep Field in 1995, and I've always been interested in that. I think that was around the time that I got my first Macintosh. And in other words, my first computer with a graphical interface, which would allow me to download images like this. And I think that was probably the first one I ever downloaded from Hubble. And there was actually a lot of people from that time who can tell a similar story. But that's not the important thing. Is this image involves, I forget some of the total amount of time that they took to basically dig this cosmic borehole, but it's something like almost an entire week of exposures from Hubble in kind of a very empty and nondescript part of the universe in Ursa Major. The director at the time was a fellow named Robert Williams, and he decided that he was going to dedicate this massive amount of time on Hubble, which is a very valuable resource, to just taking this long exposure in this apparently empty part of the universe to see what they find. Not everybody was on board on this. There was John Bacall, one of the most prominent astrophysicists at the time, wrote a paper in, I think, Nature, saying this wasn't a great idea. But they went ahead and did this, and this is what they found. Thousands of galaxies. So there's only 2 or 3 stars in this image. Thousands of galaxies looking very deep into the universe. And of course, this has led to further deep field photos. supplemented with imagery from other space telescopes such as Chandra and Spitzer. And the other part of this was that there was a massive amount of data, and usually what happens with research on these space telescopes is that somebody puts in a proposal, and if the proposal is granted, you go through the time allocation process. You have control of that data for a year, and then it becomes public. This data was basically made available as soon as they could process it. Like, this was done, I think, in December of '95, if my memory serves me right. December of the year, they were taking this data, and then over Christmas, people at the Institute were camping there while they were processing it, because they wanted to release the whole thing to the world at the AAS, American Astronomical Society meeting, which is always at the beginning of January, and they did that. So some of them had to camp over there because there were like blizzards hitting Baltimore at the time. So this is quite an amazing story, and this might shock you, but a little bit more than a year ago, a fellow named Donald Trump made a speech praising Hubble, and he talked about the deep field. So you can look it up on the internet if you don't believe me. And this of course is kind of one of the follow-ons to the deep field, and we see here some gravitational lensing. I'm not going to get into that very much with this audience, because I suspect there have been some other people who who have or will be able to tell you more about that than I could. But of course, images like this have allowed us to look even further back into history. Now, one little sidelight of my book. It's not a huge section, and actually, when I have some time, I'm probably going to write something maybe in more detail for RASC about this. But when Hubble was first launched, some of the time was made available to amateur astronomers, and it was publicized in a place like Sky and Telescope at the time, but probably a lot of people have forgotten about it. The original director of the Space Telescope Institute, Riccardo Giacconi, decided in the 1980s that astronomers, this is a public utility, this telescope. Taxpayers, paid their sweat-soaked dollars for this, and he thought that astronomers, amateur astronomers, should get a crack at it. So he formed a committee of some of the amateur groups in the United States, and put out this publication. And there were three groups of amateurs that got time on Hubble. And the interesting thing was that there was great interest at the beginning, but it kind of petered out. Also, some of the work got caught up in the spherical aberration problem. But I phoned up one of the amateurs. There's a woman named Anna Larson who lived in Washington State, not too far from where I lived, and she was like basically, kind of a homemaker, but also, did accounting and in the family business and stuff like this, but she was interested in astronomy. And her proposal for time on Hubble was accepted, but unfortunately, she never got to use the time because it was caught up in the spherical aberration problem. But she was so inspired by this, by getting that time, that she actually went and got a PhD in astronomy and is now teaching at the University of Washington. Anyway, there's sort of a number of theories as to why the popularity of Hubble amongst the amateurs kind of receded. I think one of it was to get time on Hubble, even for the amateur proposals, you had to put so much work into the proposal. It was just very daunting. Now, I think over time it's become a little easier because so much of the repetitious work is easier to do because so many things are computerized. But even so, it was just very difficult. And and when Giacconi left, his successor Williams, who is kind of the big hero of the Hubble Deep Field, wears the goat's horns on this because he canceled the amateur program. Now, that doesn't mean that amateurs are completely out of the picture. You know, anyone who wants can access the archive of Hubble data and use that data and process it. And I don't think there's been a huge take-up amongst the amateurs on it, but there has been some, and there's actually a couple of things that have popped up in press releases that have involved work by amateurs. There's also citizen science work. I think Brandon or somebody was talking earlier about oh, it would be cool to have Andromeda right next to us so we can get a good look at it. Well, there's been this project called PHAT, P-H-A-T, Panchromatic something of Andromeda, where they've been taking very detailed images of Andromeda, and they all wanted to get some help with looking at these images, looking for nebulae and other objects that you could see through Andromeda, not in Andromeda, but you can see them through Andromeda. And they couldn't figure out how to get a computer to do it, but they worked with Zooniverse to get citizen scientists to help with this work, you know, sort of similar to other projects that we've seen. So this is another thing where amateurs have gotten involved with Hubble. So anyway, we are moving towards Hubble's successor, and I've had to spend a lot of time at Goddard interviewing people who've worked on Hubble, and I've always, it's no longer there anymore, but when it was there, I would always look in on it. And of course, there's a Canadian aspect to this project too. But it's impacting Hubble because preparations are being made for joint work. They would like to get 2 years of joint work with Hubble and JWST once JWST gets going. There's also doing things like JWST is an infrared telescope, and when Hubble is no longer operational, we're going to be losing a major resource for astronomers working in ultraviolet wavelengths. So if there's what's today called an ultraviolet initiative, which means that basically if you put in a proposal for ultraviolet observations with Hubble, it will probably receive slightly more favorable rating than it might otherwise would. So anyway, these are some comparisons to how far back in the history of the universe we can look. Starting with earthbound things in the original deep field, and these other ones and what they're hoping for with James Webb. Of course, one of the iconic Hubble images is the so-called pillars of creation, the stellar nursery in the Eagle Nebula, which actually was not taken with the idea of using for an image. It was basically a couple of astronomers at the University of Arizona wanting to learn about these stellar nurseries, and they took this close-in photograph of a section or set of images of the Eagle Nebula, and then when they processed them, one of them realized this is a hell of an image, and took it to Ed Weiler, and no time was wasted in getting that out to the public. And for Hubble's 25th anniversary, they redid the images without the little backbling that you see in some of the Hubble images, which had to do with the size of the detectors that were in WIFPIC 2, and then this shot in a different wavelength. So just kind of to wrap up, there's sort of the question: well, what's in the future of Hubble? So it's going to keep on going, and the last servicing mission, they attached a little fixture to it, so that in theory, a robot spacecraft can come up to Hubble, attach itself to it, and either kick it into a higher orbit or bring it into a controlled reentry. The folks at NASA insist that they have a mandate to bring Hubble. If Hubble is going to re-enter the atmosphere, it will be in a controlled situation, even though, as we know, the odds are pretty good, even if it wasn't controlled, that there wouldn't be any casualties from it. There was discussion, by the way, about bringing back Hubble to Earth, because a lot of people have thought, it's been such a great thing, it should be brought back and shown in the Smithsonian. Now they have sort of a flight test article of Hubble in the Smithsonian, which has been kind of fixed up to look like Hubble. But actually a lot, and that's not going to happen. When the shuttle was still flying, they once asked the astronauts, well, who would be prepared to risk their lives? And this was after the second shuttle accident, I believe. Who would be prepared to risk their lives to fix Hubble so it could keep on doing science? Almost every hand went up in the room. They asked them, how many of you would be interested in risking your life so that Hubble could be in a museum? Well, almost no hands went up. And now the whole thing is kind of academic because there's really nothing that can bring it back anyway. But kind of the heart and soul of Hubble is back on Earth, in the form of the instruments. I don't know. Most of them, but not all of them, are on display in the National Air and Space Museum, and I just wandered by one day and took a couple of pictures of them. This is the CoStar instrument, and you can see these little mirrors that were used to overcome the spherical aberration problem. CoStar didn't have to stay in there for the whole life of Hubble because as new instruments were put on board, their optical trains were changed so that they compensated for the spherical aberration. So CoStar was taken out on one of those missions. And then this thing here, now you might think, well, this looks like Hubble meets Al Capone or something like this. This is the WIFPIC 2, the camera, the workhorse camera that took probably most of the famous pictures of Hubble. This is the exterior shield part. And what happened is that it was pockmarked by little impacts from orbital debris and perhaps meteoroids and things like that. But these are not the impacts. What they did is that they cut out around them and took them out for examination. So this looks much more dramatic. But you have to think that every one of those marks represents an impact on Hubble. So anyway, the successors to these instruments are still on board Hubble. Hubble is still operating, it's still going strong. We don't know how much longer it will go, and the final chapter has yet to be written, but anyway, that's what I've got for now. So thank you very much. Yes.
One of the questions that I've always wondered about when the spherical aberration problem first came to light is that if they ground the mirror in a 1G environment, wouldn't the mirror itself have changed its shape in the 0G environment?
I think they basically took that into account when they were working on it. I don't remember all the details around that question, but I mean, some of the measures that they took to make sure that the mirror was ground correctly were amazing. And then you see it was all laid low by this silly mistake. There was also some bad management in there. It's quite a story. Also, compounding the thing, of course, is the fact that Hubble is related to reconnaissance satellites. We don't know how close the relationship is, but Lockheed, which built Hubble, was also building these so-called Big Bird reconnaissance satellites, and so the security folks weren't that wild about having all sorts of NASA inspectors running around their plant. Of course, I was really interested. Is that what caused it? And it was a contributing factor. Now that I've kind of had a chance to examine it, but not the crucial one. So,
With all those strike marks, what are the chances of something striking the optics?
Well, not all that great, because they have a door over the top of it, although of course it's open most of the time. But they also have a set of baffles inside, to kind of protect against that. So, they had considered that possibility, and you know, I think there are a number of measures and limitations that, you know, which directions they can aim things. I'm not sure whether there's kind of a prohibition against aiming it in the direction of flight, but you know, they certainly are very careful about things like the sun or even the earth. You know, aiming it in those directions. So, yes.
Was not one of the things that occurred as a result of the severe collaboration problem that they started to do software development that would help improve the images that they could capture before they could put the co-star into effect?
I'm sure that was part of it. I don't specifically recall hearing that, but you know, developing better software for Hubble, I think, was kind of a constant thing that was going on. But you also have to remember that the equipment on board was kind of old, you know. Like, they have, at Goddard, they have a replica of the Hubble systems, which is called the VEST, the Vehicle Electrical Systems Test. And when I walked in there, I thought I had an acid flashback back to the 80s, you know, because they had all these DOS monitors and things like that. And you know, with all the DOS commands on it, because some of this stuff, some of the equipment on Hubble was, you know, back in the 80s. You know, they replaced the computer. The original computer was like a 386, and then they replaced it. The one that's on there now is a 486. Now, the beauty of that is that
radiation hardened.
It was hardened, and it had been tested to within an inch of its life.
Try and get a current Xeon that's radiation hardened.
Yeah, I'll tell you, you know, when you think the way they test the stuff that would go on the shuttle or on Hubble, you know, if they would test the equipment we use as much, you know, our lives would be much easier, I think.
And more expensive.
That's right. That's right. Any more questions? Okay, I think that's it.
Yeah, thanks again. Okay, so as I noted earlier, the meeting will continue at Boston Pizza, but not the one on Pevina, the one on Taylor here in Nathaniel. So, see you there, or maybe next month at the barbecue. Good night. Go ahead, take it. There it is.
Yes.
Read it.
How long did we get a member?
Last November.
We don't need it.
I have one here. What's your name? I don't know how this list. They don't put the list of options.
Oh, really?